Hey guys, Seton HVAC here. I've been meaning to show you guys how to make a Pittsburgh seam with just a sheet metal brake. I'm going to go over that with you here today. So if all you have is this $200 brake I got from Harbor Freight, you can make professional looking Pittsburghs and make your fittings properly. Some of the tools you're going to need, obviously your basic tin snips. You need a rubber mallet, rubber hammer. You need your scribes. You need one that'll go past 1 inch. On my brake, I need to be able to scribe 1.5 inches, so you'll need that type of scribe there that's adjustable. You get your basic scribe that goes from 1 inch down to 1/4 for all your basic scribes. Bar fold, a regular hammer, and a screwdriver. These are the basic tools that you'll need to make this Pittsburgh joint for sheet metal transitions, sheet metal rectangular duct. Anytime you want to make a professional finish, and not do what I see some guys do on the internet, where they make just an S lock joint. That doesn't look very good, especially if you're going to leave it exposed. If you're wrapping it, yeah, seal it, wrap it. It doesn't make a bit of a difference. But if you're doing something exposed and you want it to look nice, make a Pittsburgh. It looks the best. Let's grab these tools and let's get started. Okay guys, well, let me show you how you start this. So let's do like a real job scenario here. I need a 20.5 by 15.5. I used weird dimensions on purpose to show you that you can do this in the field. I need a 20.5 by 15.5 piece of duct, 12 inches long. So first thing you want to do is you want to figure out, okay, what do I need to do for my stretched out pieces? Now, stretched out pieces means that you are, okay, I got distracted for a second. So what you want to do is figure out what your stretch outs are. And if you're in the field, you're on a standard 3-foot brake, you're going to have to do it in 4 pieces. Now, pretend this is a weird transition you need for a gas furnace change out or an AC add-on or something. These are just dimensions used to show you the basics. So what you want to do, and I have to do this with my Harbor Freight brake because 1.5 inch Pittsburgh works better. A standard stretch out on a Pittsburgh machine, if you buy one of those $5,000 machines, is 1 inch for the Pittsburgh, and then you're putting a 1/4 inch male in, to go into the Pittsburgh pocket. In my scenario, it's going to be 1.5 inch for the Pittsburgh, and then 1/2 for the male that goes inside the Pittsburgh. So I always like to do the Pittsburgh on the sorry guys, I keep getting distracted by pets and kids and whatnot. Let me know if that makes sense to you. Adding the 1 inch for the I call it the pocket side. It's the side with the 1 inch. It's gonna, or the 1/2 inch. It's gonna get bent up on each side. And then for this one, you want to scribe out your 1.5 inch for your Pittsburgh side, your Pittsburgh seam that you're gonna make with just your hands and a brake. It's important to note, you want to only draw your line for the Pittsburgh on the outside, because you do all your bends from the outside. The only reason this 1 inch line is here for your duct connection is just so you can notch it from this side. Then you're drawing this line on the other side. You don't need to. And you do this at about I call it a 70 degree, maybe a 60 degree notch that way, and then you notch kind of like that. You get a feel for it as you work with the stuff. Then I'll show you how you cross break it first. Bend this up with just a rubber mallet in your brake for the most part. Mine's kind of tough to do, but I've been able to figure out how to do it. If you have a better brake than what I have, it's gonna be a lot easier for you. I'm just trying to show you how to do it so it can save you from having to buy a Pittsburgh, because they're spendy and not everybody has room for them either. you can take this Harbor Freight brake with you into the field and do all this. So, and the same thing with this side. You're just going to cut it about 70 degree. This one's pretty straightforward. This stays just the way it is, and then you're going to bend these up at a 90 degree. Now, if you're doing a S and drive, obviously, just build the duct first. It's kind of easier, and then just take your bar fold, and then you can bend your drive ears over after you already have this all hammered together and done. Really nice way to make this stuff look professional with minimal tools. Very, very inexpensive tools at that. So I'll be right back, and I'll show you how to notch this up and build this thing. All right, guys, so we're back here. I'm going to show you how this gets notched. So if you take a look at this real close, so yeah, it's about I'd call it a 75 degrees. 60 to 75, it doesn't matter that much. But that's how you want to notch your corners. So we have our 1.5 inches here for our, let's turn them the other way. It's a little easier for you to see. And then always put your dimensions, or not dimensions, always put your side that is. So this is our inside, and I said that wrong. So this is our long side. Okay, this is our it's a 20.5 by 15.5. So here's our 20.5 here. There's our 1 inch flange, and then there's our 1/2 inch pocket to go inside the Pittsburgh. So that's how you want it to look before you go over to the brake. Let's look at the other piece. So here's our 15.5 side. So remember I said you want to add 3 inches, so it's 18.5 total. So you got your 1.5 inches here. You have your 1.5 inches on the other side, and then we have our 1 inch. That's for our duct connection. You do whatever you want with this when we get it all put together. If you need to bend drive ears, I showed you how to do that. So, and this is the outside. Okay. So if we flip this over, you don't have your line for your 1.5 inches because we're not bending it on this side. We have it there in case you needed to bend a tweak or something, if it's an offset fitting. We can get into that too if you want to do that on the next video, sheet metal video. But this is how you're going to lay it out. So this is your outside of your shorter side. You're going to make 2 of these. And then you're going to make 2 of these. You're just making 4 sides of a 20.5 by 15.5 inch duct. I think we're ready to head over to the brake. All right, so let's take our first piece over to the brake. This is our short side. It has our Pittsburgh side on it. So let me show you how we put this together. So first thing you want to do is stick the whole piece inside, like so. Put it right up to the line. Okay, see that? And then you want to grab your rubber hammer right here. And all you're going to do is just tap that over. Let me show you. Okay. Then what you do is take your brake and bend it up. Okay. Like that. Okay. So now what you have is you have a piece that's going to hang over a little bit longer than that. That's what you want. That's what gives you your pocket. So then you're going to take your mallet and just hammer that all the way. Now, what you want to do, now my brake's not the best, so I have to flip this over So I have to pull it out of the brake, flip it over, and then all you're going to do is just push your brake down. Just like so. Then you can flip it over and finish it off. So let me show you what you got here. So you have your Pittsburgh seam all the way across now. For some reason that one didn't do real straight for me. But the finished product will look fine. It'll be a little bit off. Let's see if we can do better on the other side. That over. Sure you're on the line. Rubber mallet time. Bend it all the way over as far as you can. Then you're going to take your brake, bend it up. Take your mallet again, and lay that down all the way as far as you can. Okay, that looks a lot more even that time. I just probably was in a rush on the first one. Then flip it around, stick that end in, and hammer it down. Now you have a perfect Pittsburgh all the way across. See that? So now that piece is prepped. You do this twice and you have two sides to your fitting. Let's go grab the other side and let's make the pocket side. Okay, so now we have the pocket side here. This is the part that goes inside the Pittsburgh. We got our 1/2 inch there. Let's bring it over to the brake and let's show you how that's done. We don't need that anymore for this video purpose anyway. So let's go over. One thing I didn't show you is the cross braking, so let's do that first. So all you do is you meet your intersection on the one side of your two dimensions, your 1/2 and your 1, and then you bring your other side over there, and then just give it a little bit of a bend with your brake, and then do the opposite corners, and you just put an X in it. What this does is stiffens the duct up so it doesn't tin can make noise when the blower of the equipment comes on. So same thing, tighten it down, and then just give it a little bend and give it a little crease. And you see what that looks like, just like so. Then all you're going to have to do on this piece is just bend your two ends up 90 degrees. Really simple. You can do it by just putting that in. You can slide it all the way. It doesn't really matter. For ease of video, I'll just slide the whole thing in and put it on the 1/2 inch. Like so. And then just go to 90 degrees with your brake. Pull it out, and then you get your other side on the line there. Bring your brake down, and then you're just going to bring the whole thing up 90 degrees. So, you see that? 90 degrees on both sides. That's your 1/2 inch. Let's go back over the table for some assembly. Okay, so we're back for some assembly. So all you're going to do is take your Pittsburgh side there. You got two of these, and all you do is put your 1/2 inch inside of there, like so, and then take your regular hammer and you're just going to beat that over. All right, guys, so here's the finished product of the Pittsburgh. So you can see, I mean, it's basically what a sheet metal shop would do. One thing I did do wrong, I'm not used to doing this on video, is I should have crimped that down more in the brake. The actual Pittsburgh itself made my joint kind of loose, and I didn't cross break that side, but you get the gist of it. You want to cross break all 4 sides. You're gonna do this in 4 pieces. Key points are, you know, add 1.5 inches to each side on your Pittsburgh side, add 1/2 on your pocket side, which is what I call it. Depending on the brake you have, if you want to get a $200 brake like I have, you can get this done. You know, cinch that down more because it's kind of loose. But you'll have professional fittings done in the field that you know, make you look like you got a nice sheet metal shop. Even if you're a one-man band like me. You can also, you know, I always stock a little acetone for shining up my metal. Just make sure you only use it on the outside because you don't want it in the airstream. But, you know, something that gets your Sharpie off of there, polishes your duct up, makes it look really nice. I think it looks good. I mean, it looks a lot better than doing an S-lock slip joint, or what I've done normally is just a half joint, put in it, and then I have to screw it together. But I think the screws look tacky, and this will seal up 100% too if you do it right. So you know, let me know in the comments if you got something better that you do. Doubtful, because I don't see anybody doing these field Pittsburghs with just the brake in the field. I think it's the best way to do your joints, and you'll have quality looking work, and it'll look good. If you screw up a side, remake it. It only takes 10 minutes to remake a piece of metal. Don't rush it. Make it look good. You know, you're installing something that might be there 15 or 20 years or longer, so make it look good. And other thing I wanted to mention too is I always like to use at least 24 gauge metal for my fittings. It just, you know, the cross break helps, but sometimes even with 26 gauge metal with a cross break, you still might get a little tin canning, especially with larger fittings. So you know, it's always a good rule of thumb is use 24 gauge. It costs about $5 more a roll, depending on where you buy it from, maybe 10. But it's well worth that extra cost for eliminating issues that you might have with lighter gauge metal. And some of the distributors that you buy sheet metal from will give you ductwork that is not up to snuff as far as the gauge of the metal and the quality of how it's put together. You'll fight some of it. So I like to build my own stuff if I can. Obviously, stock rectangular duct and whatnot, I have to buy it from it's just I don't have a shop to build stuff in that can mass produce ductwork. So but as far as singular transitions and whatnot, you know, I can load up that little 3-foot brake. I can load up a couple rolls of metal, you know, bring my S-lock and drive for connecting everything. I have a couple of plastic sawhorses and a piece of plywood I can load in my truck too, to make myself a little table. I usually just use the old furnace that I pulled out, or the old air handler that I pulled out for a table, and it works pretty good. You know, I can get stuff done. It's fun once you get really good at it, because you're able to save yourself some time too. I don't have to call fittings into a sheet metal shop. I can just go to the job, get the whole thing done, all by myself, which is what I've been doing for almost 30 years now. Well, probably 25 of it building my own sheet metal fittings. Let me know if you liked the video. I appreciate it if you'd subscribe, and I'll see you on the next one. Hopefully you learned something here.
You understand? I don't like it. I don't like to think about it.
Okay guys, so there's 3 key points that you want to address when it comes to proper duct design. Number one, proper airflow. How do we determine the proper CFMs needed to be delivered to each space, and how do we come up with that number? Okay, I'm going to show you how we come up with that CFM value to properly heat or cool a room at its design conditions. Point number two, velocity / noise. Now, what does that mean? So not only do we need the proper airflow, we need that air to be at the proper velocity. If you do not maintain the proper velocity in a space, whether it be a commercial space or a residential space, you will have noise and you will have complaints from the customer. So I'll show you how to make sure that that's not an issue and to fall within the proper parameters on velocity and surface area. Sorry, I'm saying that wrong. Surface area of your filter. So, which is very important, because that is a number one noise complaint from customers is face velocity through your return grill or return filter grill. And then three is cost. How do we do this the most economically to deliver this air? What products are we going to use to make sure that we have the proper airflow and velocity through our ducts, through the duct system, without breaking the bank? Because obviously, if money wasn't an issue, we could use the best products, and it makes it a lot easier. But sometimes you got cost constraints, so we want to address that too. So I'm going to show you how we do all three of these things. You requested this manual duct design class, so I'm going to keep it very basic and keep it simple for you, so I'm not just bombarding you with a 300-page book that can a lot of guys aren't going to go through a whole book and do that. So I'm going to go over the basic points with you on how we do this and how I go about doing it simply and efficiently. So I'll be back. Okay, guys. So give me a second here, we'll get this started. So, 1 second. Okay, so bullet point number one, okay, was proper airflow, okay? How do we determine proper airflow? First thing you need to do is do a manual J. And we'll go over manual J probably after this video. So we're kind of going backwards here, but somebody requested duct design, so we're going to do that. So manual J, and you want to do a room by room load calc. This is on a new job. You need to determine what duct size goes to each room, how many CFMs each room needs, okay? So how do we determine that? Well, first thing we determine by our heat loss is what CFM does each room need, okay? So in order to get our CFM, we need to know what our BTU is, right? So let's say that the room needs 3,000 BTUs. That's determined by your manual J, okay? That's just a rough number. Some rooms require more or less. This is just for the sake of this video. So how we determine CFMs is based off the BTUs. So 3,000 BTUs. So there's an equal here. So BTUs equals CFM times 1.08 times your delta T. Now we always shoot for 20 degrees delta T on a air conditioning system. Most areas of the country are going to most areas of the country are going to have a higher cooling load than heating load. So you're going to want to go by that, not go by your heating side, which would be a different delta T if you're doing a gas furnace or whatever. You always want to go by this. That's going to give you your CFM needed. That's why we put dampers in all the ducts, so we can damper it down in the seasons if need be. Otherwise, you have too much airflow in the heating season. So 3,000 BTUs based off this formula. BTU equals CFM times 1.08 times your delta T. So that converts to, okay, we need 3,000 BTUs equals our CFM, which is an unknown quantity at the moment, times 1.08 times 20, which is our delta T, okay? So that converts to 3,000 BTUs equals, let's call it X, we don't know yet, times 21.6. That then converts to 3,000 BTUs equals somewhere between 138 to 140, there's percentages in there, times 21.6. So this is how many CFM we would want for that room. Now, how did we come to that number? So if you take 21.6 and divide it by 3,000, that gives you this number. It's like 138 and some change or something, 139, somewhere in there. But that's how you get that. Now, take a picture of this. This makes complete sense. This is a duct design part of it. This is only part one. We're going to get into how do you find duct that's going to equal this 138 to 140 CFM for that room, and how does it go with the entire system. Let's say the entire system needs 36,000. That's where we'll start on the next video. I just wanted to do this first. Hopefully it's not too jumbled, guys. I'm trying to teach it to you properly, but it makes a lot of sense. And you'll find this on that slide rule that I have. Your BTUs will equal X, which is your CFM, times 1.8 times whatever your delta T is. And that's how you do this, right? So let's go over it one more time. 3,000 BTUs equals an unknown quantity times 1.08 times your delta T, which we're going to use 20 because we're doing it for cooling. So 3,000 BTUs equals an unknown quantity times 21.6. You would take this number and divide it into that 3,000 BTUs, and that gives you your CFM for that particular room, okay? You should do this first once you have your heat loss done, and then we can get to designing the duct, because you want to make sure this CFM is delivered to each room properly. So on the next video, I'm going to erase all this, and I'm going to show you guys how you start with your duct and how you taper your duct down as you get rid of those CFMs. And you also want to keep your velocity at a certain rate too, okay? And there's recommendations, I think it's SMACNA and ACA that recommend velocities different for residential and commercial, obviously, because residential is a little bit quieter, commercial you can go a little bit noisier just because all the background noise. So this is a beginning. Let me know if I need to explain it a little bit better. We'll get into this more as we do the actual designing of the duct, and I'll try to get a better. I might use this whole whiteboard, but I'm using half because I have some other personal information on this other side. So let me know if this makes sense to you guys. But this is where you want to start, right here. This formula. This is X right now too, because we don't know what that is until you do your heat loss. You put your value in there, and then you have these two numbers that are fixed based on you're always going to size for cooling in most regions, and then this is going to be an X too. So you don't determine this, we'll determine this, okay? In this instance, 3,000 BTUs is going to be, if you size it for the cooling side, you're going to need 138 to 140 CFM. Off the top of my head, if it was my house, I'd probably do 7-inch rigid or 8-inch flex, and you always want to put dampers on all your runs to make sure that you're dampering stuff down, and you want to dial it in with a flow hood, which I don't do on every job. I'm a one-man band, but I can get it close enough where my customers are happy. So. That's part one. Part two I'll probably do tomorrow, and part three might wait until next weekend. But I'm going to do 3 parts and show you how all of this comes together based on the first portion of this video where I showed you the 3 steps to duct design. So thanks for watching, guys. Good morning, guys. Seton HVAC. It is Tuesday, December 31st, 2024, New Year's Eve, or the day of New Year's Eve anyway. I was going to quit doing these little intros because I think people kind of tune out and they get to the meat and potatoes of videos and want to see the actual HVAC work. But I wanted to do one today. So I had more planned for today as far as work is concerned. But my wife had to go into urgent care this morning. She had a pain in her stomach. She thinks she has an ulcer. Probably the stress of dealing with me. But kind of messed the day up. So she had to go in, and she was in there a while. So I had to stay with the little one this morning. So I wanted to mention that, why I don't have more of a video today. I'm probably going to do the part 2 of the duct design for you. But I'm going to pick up a check from a customer. I'm going to get my truck gassed up. But I also wanted to talk about how we're going to be killing it this year. 2025 is going to be the best year yet. My goal is to have at least $800,000 gross. And as a one-man band, you know, with my brother helping out here and there, I think that's pretty good. If I can do 800,000 gross, you know, I can take home quite a bit. So that's the goal for 2025. Want to talk about that real quick and just let you know why I don't have much content today. I won't ramble on any longer this morning, and I'm going to attach part 2 of my duct design. Please, I'll put part 1 in the description for you, so you can see that. So, thanks for watching, guys. Okay, guys. So we're going to do this in the most basic forms here. I'm not going to bombard you with all the information. If you really want to learn duct design, you need to go out and buy the Manual D Manual D for Residential Duct Design book, which you can find on Amazon or pretty much anywhere. Just Google it. So if you need a link to that, let me know. So the first thing that you want to do to design a proper duct system that you know is going to work, well, before you do this, is you need to go into the manufacturer's blower data and find out at what external static pressure will give you the design CFM that you were looking for, based on the video that I showed you yesterday, how to convert your heat loss and gain analysis into CFMs. Once you know how many CFMs that you need, then you're able to go into the manufacturer's blower performance data and find out what external static pressure will produce the CFM that you need. Does that make sense? Makes sense to me. If it doesn't, let me know. So once you know what your blower performance data is and what CFM it'll produce at that, then what you want to do is measure out your duct system. Okay, so first thing that we need to know is what is our total equivalent length of our duct system. Okay, and I'll get into this in a second. Let me show, but I want to show you how we determine where we put the friction rate on our ductulator, our slide rule. Okay, we don't just go 0.1, we just don't go 0.08. There's a science behind it, and there's an equation that gets us to that point on our ductulator where we can use it properly instead of guessing. So that's over here, and we're going to get to all this stuff too. But what it is, so this is a friction rate. This is what you're going to pick on your ductulator, your slide rule. So that friction rate equals your available static pressure times 100 feet of equivalent duct divided by your total equivalent length, which is that total equivalent length. Okay, TEL. How do we determine that? Let's go over here to our components. So in the Manual D Residential Duct Design book, let me show you guys the book here real quick. So this is the book, Manual D Residential Duct Systems. Okay, so if you thumb through this, there's a section that tells you what your, sorry about the lighting, guys, kind of doing this on the fly, but I'm trying to keep it basic and not just bombard you with a ton of information. It gives you different fittings that you'll use in the field. It gives you total equivalent lengths for those. Okay, let's show you the basic ones that you're going to run across the most often. Like here you go. So you know, you got your 4 or 5 piece elbows. I mean, there's even a different total equivalent length for a 3-piece elbow, but it tells you what that equivalent length is, what it adds to your total equivalent length of your entire duct system. Okay, so it even shows you like pan joists, pan return airs. Shows you, you know, if you have a return air that deadheads into a duct, what that equivalent length is. 55 feet. So that's a horrible fitting. I mean, that's cutting into your budget for on your static pressure right away. So that's why it's really important to do good fittings off of your equipment. You know, even just adding like a little radius here cuts that down to 35. So you just cut 20 feet of equivalent length of your duct system just by eliminating that and putting a tapered edge there. So lots of cool stuff here, guys. Like how do you take off? How you do your takeoffs? If you flare them, you know, it's less than if you do a straight piece. That's actually 40 and 40. That's kind of weird. Shows you if you have a round coming off what that is. So lots of cool information in this book, guys. And you know, even shows you like different boots, different radius fittings. It's like an old OG fitting there. You know, like a wall stack. It shows you every fitting that we'll ever run across in the trade. Takeoffs on trunk lines. So anyway, we'll get back to this stuff, but it's a very awesome book. If you really want to make your customers happy on a new build and you want to do things right, follow this to a T. So let's go back over here to the dry erase board. So I kind of mocked up here, you know, a fictional system, but you know, a scenario that you may run across. So the first thing you want to do is draw it out and get all your measurements on where each run's going to be. What we're trying to do is we're trying to find what the longest one would be, and that's what we're going to size our blower. What the longest total equivalent length run is, okay? And you know, this is all fictional. You'll want to do the math and figure out exactly, you know, where you're losing your length and whatnot. So if you come over here, so let's say we're going to say this is a furnace standing up with a plenum and a takeoff, okay? So if you come over here, that's equivalent to 35 feet per the book, right? Let me get the lighting better here. 35 feet. So right there, we have 35 feet before we've even begun, okay? I'm gonna call this, well, this is the return, sorry. So the supply is 35 feet just right here. Then you can start adding up all these lengths, okay? So I'll be back in a second. I'll show you how we add all those up. Okay, guys, we're back. So I added a couple things here I was missing. Okay, so what we want to do is we want to find our furthest, well, let me say that differently, our supply run that has the most total equivalent length, okay? So what you want to do, let's say that this fitting coming off here for your supply on your equipment is equivalent to 35 feet, okay? Then you're going to add 15 for that trunk run there, so 50, and then 25, 75, I don't know, was that 90? Let's say 90 to this one. Let's say this is our longest one, okay? 25 feet total equivalent length for that takeoff, so it'll be 115. And then you got, let's say your boot is 10 feet of total equivalent length. Does that make sense? So each fitting has a total equivalent length. So your boot, your takeoff, you know, your straight trunk run, that's basic feet, and then whatever you're losing to do your fittings here by your equipment. So that adds up to 125 total equivalent length on your supply air. Let's do our return because we're going to add them together, because our total equivalent length equals our return and supply added together, okay? So let's say, you know, our return air is coming up, there's an elbow, and it's going to do another elbow, do something weird, okay? So let's say that adds up to 90 feet. And then we have 40 feet of pipe, and then let's say our C box and how we tap into that adds 30. So 30 plus 40, 70, plus 90 would give us our return air total equivalent length of 160 feet. So then what we do is we're going to add both of those together. So 285, okay? So we're going to put that number down here. I will be right back. Okay, guys, so I went ahead and wrote that in there so you don't get confused. So FR is friction rate, and then I wrote a 285 in there. Now, I know a lot of you'll just go out and buy like the right soft programs. It does all this for you. It'll draw your duct out for you. But I don't think it's very accurate. Plus, I think there's a lot to be said for doing it by hand, because you can tweak it and make it, more as built, as opposed to just a program spitting it out, because once you get on site, it changes, trust me. And of course, you want to verify your static pressures and stuff when you're done installing the system. So let's go back to this formula here. So available static pressure times 100 over 285 will give us what we need to put on our slide rule for sizing this duct, okay? How do we get this number? I'll show you. So let's say, this is a smaller system. We have 8 runs here. Let's say it's a 2-ton system, whatever. We want 800 CFM, okay? Well, this is where you go back to your manufacturer's equipment data and find out what external static pressure gives us 800 CFM. This is all fictional. So let's say on this piece of equipment, that 0.67 ESP, external static pressure, gives us 800 CFM. Well, we have a budget of that total, okay, with our duct system. So what we need to do is, sorry about that, guys. My dog likes to sneak into the garage here and try to get into the garbage, the trash bag that's out here. Oh, trying to do this stuff on the weekend when everybody's all rambunctious on a Sunday. So let's continue on here. So available static pressure. How do we come up with that? So what we need to do is find out what component losses that we have. And this is all in the book, guys. Go get the book. It's an awesome book. And read it thoroughly. There's a lot of good information in there, but I'm going to go over it with you real quick. So you want to find out what your component losses are, okay? And the number's already there. So let's say your coil has a static pressure loss of 0.2. Your filter static pressure loss of 0.15. Supply grill 0.03. Return grill 0.03. And these are pretty standard, actually, if in the component section of the book, it tells you what your losses are in certain things. Let's say you have a balancing damper in there, that'd be another 0.03 loss. So those all add up to, hold on, that's wrong. Those all add up to 0.44, okay? That's, 0.35 plus the 0.09. So your component losses are 0.44. So then what you're going to do is take this and subtract that from it, okay? So that gives us an available static pressure of 0.23, okay? So let's write that in there. So take that off there. We're going to do some math here. So let me erase all this because I think you got this. Take a picture of that if you want. Like I said, this is a quick overview of how to design these duct systems. I'll just scan this whole thing for you real quick. I've done it so many times. I know it's hard if you've never done it before. Let me fill in these values and then I'm going to write it all out here for you and I'll be back, okay? Okay, guys, I cleared this and wrote this out for you. So remember, this was our available static pressure. This is basically the budget we have in our duct system, okay? So it was 0.23 times 100 over our total equivalent length of duct, which was 285, okay? So that gives you 23 over 285, and that converts to 0.0807, or just 0.08 on your slide rule. So that's how we get our friction rate on our ductulator. It's not static pressure, it's our friction rate that we have. It's basically, I call it a budget for our duct system, okay? So tomorrow, or actually sometime this week, I'll finish this out. I wanted to do this in 3 parts, and there's stuff missing, guys, okay? This is just the basics. What I'm going to do is show you how to utilize this to turn these into duct sizes, okay? It's very, very easy to do. It's not just a matter of putting your slide rule on 0.08 and rolling for it. I'm going to show you how you want to do this extended plenum system and reduce and do all that properly to keep your velocities where you need them to be. All right, guys, distraction number 5 million. I'm trying to do this on a Sunday, so I'm gonna get back to the family. We're gonna go grocery shopping and stuff. But yeah, let's reconvene. I'm gonna show you how to turn all of this into duct sizes based on this by knowing how to do all of this math. Okay, it's very important. You don't want to just guess. Yeah, you could have put just 0.808 on and you got lucky and it worked, but it's not always going to be that. It's going to vary on each duct system depending on how it's laid out, what type of fittings you have, what equipment you're using, you know, how you build your takeoffs. Everything works together. It's not just slamming it in and hoping it works. So I'll be back tomorrow, and I'm going to show you how we do a real world duct sizing based off these formulas that we just did. So I'll see you guys back here, not tomorrow, probably sometime this week, might even be next weekend, because I'll be doing my ride along videos this week. So stay tuned, guys. Hey guys, how did we get to the point here where we're talking about trash bags as they pertain to HVAC? How did we get here? So this is the culmination of my 3 videos, and I wanted to put it at the front of this video so it keeps you intrigued on how we got here. If you don't have a flow hood, this is a cool way to check the CFM of a register. You tape your trash bag over your register opening, okay? So a standard, like a Husky construction cleanup bag, is 42 gallons, okay? 42 gallons is equivalent to 5.61 cubic feet, okay? So what you do, because flow hoods are expensive, you don't spend $4,000 on a flow hood, do you? Well, we can do it this way. So let's say the bag fills up in 5 seconds, okay? That's equal to 1/12 of a minute, or whatever this number may be, okay? So what you do is you take 60, which is a full minute, and divide it by X, however long it takes to fill up that 42-gallon bag, and you're going to times that by 5.61. That's 1 cubic foot, okay? So let's say it does take you 5 seconds. So that's 60 divided by 5 gives you 12. You times that by your 5.61, that's your cubic feet per minute, and that gives you 67.32 CFM. You can do this with any size bag. It's easier with a big one because it's going to fill up real quick. So what you do is have your helper go turn the thermostat on to cooling, have your bag taped over your register, and do this. Time how long it takes to fill up the bag. Once it's full, it's going to pop your tape loose because it's pressurized, right? So do it until your bag's pressurized, and then time it, and this number will change. So use this formula, however long it takes to fill up that bag, put in where that X is. So it'll be 60 divided by whatever times 5.61. That will give you your CFM, and that's on a 42 gallon. You'll need to convert if you have a different size trash bag. You'll need to convert this from gallons to cubic feet, yeah. This number will change based on how big your trash bag is. Just punch it in. They got formulas online. You know, 12-gallon would obviously be different, etc. So thought you guys would find that cool. Nobody wants to buy a flow hood. I sure as heck don't. If I need to dial in somebody's CFM, this is really easy to do. You just tape down a plastic bag over your register. So thought you guys would think that's cool. Let's get on to the final duct design video. Okay guys, welcome to part 3, the final part to this duct design class that I put together for you. So here's where we're at. So if you watch the previous videos, we figured out how to get our friction rate. This is the value that you're going to put on your ductulator, okay? 0.07, I'm just choosing that for the sake of the video. This number is going to vary. It could be anywhere from 0.04, 0.05 to 0.1, depending on how your duct system's designed and what static pressure you're going to use, and what your total equivalent length of your duct is going to be. So This is going to be a 3-ton, 1200 CFM system, okay? I'm going to show you how we come up with all these duct sizes and how we lay this out. So right here's our air handler, okay? 1200 CFM air handler, whether it be a gas furnace or a standard air handler, electric furnace, heat pump. So how do we determine these sizes of the duct? Okay, so what you're going to want to do is put your CFM on your first section of the duct before you have any of your supply takeoffs off. Okay, so that's going to be 1200. So what gives us 1200? Well, you put on your slide rule 0.07 friction rate, and at 1200 CFM that gives us 16-inch hard pipe or 20-inch flex. So this section is going to be that size. Okay, so then what you do is, obviously every system is going to be different. So let's say we have 2 takeoffs here. One of them needs 100 CFM, one of them needs 40. Now this is all based off our heat loss analysis and converting those BTUs to CFM. So this is going to vary quite a bit from system to system. I just did these numbers randomly to equal 1200 CFM. Obviously, sometimes the rooms each need a little bit different, so you always want to put dampers in each run too, because you're going to need to dial these in. So anyway, so you got 1200 CFM, that would be a 16-inch hard pipe or 20-inch flex. Then you would take these CFMs off, which would be 140. Okay, then you can put a reducer here and reduce it down if you can. So at 1060 CFM, because remember we lost 140, you're going to be at 1060, 1200 minus your 140 is your 1060, and then so that's going to be 16-inch hard pipe or 18-inch flex. Okay, then let's say we have another 2 takeoffs that takes another 180 CFM off. Okay, so you're going to reduce it again, and this time you have 880. Oh, so the 1060 is 16-inch pipe or 18-inch flex, just based off of this value. Okay, your friction rate. Then you continue to taper down, so 880 would still be 16-inch or 18-inch flex. I just put the quotations because it'll be the same. 2 more takeoffs gets us down to 790. That would be 14-inch or hard pipe or 18-inch flex. 2 more come off. I'm going over this real quick because it's kind of monotonous once you get past the first one. Then you're down to, because you're taking that 350 off of that, so you're down to 440. That gives you 12-inch hard pipe or 14-inch flex. And then your last 2, obviously, you have 300 CFM left because you have 200 and 100, would be 10-inch hard pipe or 12-inch flex. When you're doing this, it's very important to reduce it when you need to, because that maintains your velocity that you need, okay? If you don't do that, you're not going to maintain the velocity, and the air's coming out is not going to be the proper CFM. So you got to maintain the velocity. Also, you don't want to taper it too soon, or you have too much velocity and you end up with a duct system that's too noisy. So you don't want that either. One thing I want to note, when you take your last run off of your trunk line, okay, this is what's called a reducing plenum duct system, which is pretty common in most new builds. So that's kind of what we're focusing on here. You want to make sure that after your last run, you have 18 inches of duct past your last run. That's so you can build up back pressure. So what's going to happen is the air is going to fill everything, it's going to hit this, and then it's going to pressurize, and it's going to push the air out through the ducts. As long as you design it right, it's going to push them out properly. You're going to have a damper on every run, and then you dial in each CFM. So how do we determine these branch run CFMs? Same concept, 0.07 friction rate. So based on that friction rate, 200 CFM is going to be 9-inch hard pipe or 10-inch flex. Okay, 100 CFM is going to be 7-inch hard pipe or 8-inch flex. Let's go to a different size. 150 CFMs, 8-inch hard pipe, 9-inch flex. Now, one thing that you want to do when you're building these duct systems too is some of the best takeoffs of these are the 45-degree cone saddles. So they're kind of a fitting that looks like this. It's got a little bit of a cone there, and then it shoots off at a 45-degree with your round throat on it. That's going to give you your best flow into each run. I strongly recommend doing that when you're doing a round system. They make a they make a flat, like let's say if this was rectangular duct, they make a flat airtight takeoff that works good, but I think they just make straight ones. What you want to do in that instance then is put a 45-degree elbow right off, and that'll help your airflow. What else here? So obviously you want to seal everything 100%, and you want to insulate it for whatever the whatever your jurisdiction tells you to. So let me show you something else here. So on our return, how do we come up with this? So same concept. 1200 CFM is going to be 16-inch hard pipe or 20-inch flex. There's no getting around that. That's the two sizes based off this friction rate that you have to have, okay? So how do we determine our grill size? It's 20 by 25 on a 3-ton system. Let me show you that. Okay guys, we're over here at our little cheat sheet for doing your return grill area. So the formula is 1200, which is our CFM, that would be a 3-ton system, right? Divided by 350, okay? This is a formula. So it's X, which is your CFM, divided by 350. Will give you a number, a different number each time based on what CFM we're looking for. That converts to 3.43. Then what you do is you take that 3.43 and you times it by 144. And that gives it, and the reason you're doing that is this is your square footage of your grill. And we need to convert it to inches, so you know, because they don't do it by feet, they do it by inches. So this converts it to inches by timesing it by 144. So 144 times 343 equals 494. That's 500 square inches, okay? So we know that 20 times 25 is 500 square inches, so that would be a perfect size. You could come up with any size of grill. You know, let's say you got studs that are 16 on center, so you go 16 by, I don't know, 30 something, 32 would get you there. And that would give you your 500 or 494 that you need. You know, obviously they don't, you'd want to do something that's 500 because 494 is a weird size. And then on all of these, this formula is basing it on the fact that you have a 70% grill area. You know, you don't have a full 20 by 25, but it already takes this off in that formula. So check with your grill manufacturers and make sure that you have that free space area in that grill. A lot of guys will put those honeycomb return grills in, which is a lot better. They have a higher percentage of a grill area than a standard stamped return grill, like what are they, the 1050s by Shoemaker. So that's the formula you want, guys, for sizing your return grills. You know, this is the CFM of your system. All these other numbers are going to stay the same, okay? You're going to divide by 350 and then times that value by 144, and that'll give you your square inches, and then you can size your grill based off that. But also look at your manufacturer's specs and make sure that you have at least a 70% grill area. If not, you'll have to adjust this number, okay? You want to upsize it a little bit, you know, based on this percentage. So hope that makes sense to you. Let's get back to the duct system. All right, guys, so let's summarize this real quick. So you always want to start out with your total system CFM and reduce your plenum. You know, everyone's going to be a little bit different. Some systems you might reduce it after 4. Just depends what makes sense for changing your duct sizes. As you can see, after this first takeoff here, the hard pipe size doesn't change. So you're just going to do this. You know, there'll be no reduction here. That's why it's important to maintaining velocity. You're going to have dampers. That's going to maintain your feet per minute and maintain your CFMs. So do a nice taper down to make sure that you get that air to your last runs here, because remember, this number here is based off your longest run, okay? You want to make sure that there's enough air left to get your CFMs to your furthest, your run that has the most total equivalent length. So let me know if all this makes sense to you. I went over the grill sizing. You know, most guys are going to run flex up through an attic, so always make sure you're changing your size of pipe if you're going to do flex. This whole thing could be flex too. I'm not against flex, but just know that you need to pull it really tight in order for these numbers to in order for that size of flex to work. You know, there's going to be a lot more compression with flex. You want to make sure you avoid sharp turns with it. In a perfect world, we do every system in all hard pipe, which I strongly recommend. In commercial, you know, they don't they don't allow you to go more than 5 feet of flex. So I think residential should adopt that too, hard pipe and then just a little flex at the end, just for sound attenuation. So that's basically it, guys. If you have any questions how we got to this point, you know, you have all 3 videos. You should be able to design a duct system from scratch now, just with a pen and paper. You shouldn't need any programs. That's how I do it. Sometimes, you know, it's faster to use the programs, obviously, but I learned how to do it this way, and I'm kind of proud that I can do that, and you know, helps keep our mind sharp too. So thanks for watching, guys. If you got any questions, let me know. Hey guys, Seton HVAC here. So what do these numbers here mean, and why can they help get you out of a bind on a job if you're out of pipe? And let's say the parts house is closed, you don't have any, and you need it to finish a job. Let's go over this. So if you know what this is, and you know what this is, you can build a piece of pipe out of a straight piece of sheet metal. Now, knowing this dimension is just the start of it, but we'll get a little deeper in. So this is pi, okay? This is what determines your circumference of a circle, right? So you can use 3.14, which is okay. What's even better is 22/7, because that's a more accurate number, okay? That's pi. So let's say you have 6-inch pipe. 6-inch pipe converts to 6/1. You would times that by 22/7, your pi, gives you your 132/7, right? That equals 18.85. 19 inches is close enough. If you cut a piece of metal at 19-inch width, that is going to be what you need for your circumference for 6-inch pipe. If this was 8, you'd do the same thing. 8/1 times 22/7 would give you a different number. You know, you'd be, I don't know what that equates to, 20 something, the low 20s, okay? So if you know these numbers, it can really get you out of a bind, or you could even do the math on all your basic sizes of pipe and keep yourself a cheat sheet on what you need, okay? So using these numbers, I'm going to show you how to make round pipe out of flat stock. You know, maybe you're out of round pipe and you got, I need like, you know, I need another 12-inch piece, or, you know, it's not going to quite reach. If you have like just flat stock laying around in your truck, you can make a piece of round pipe and get yourself out of a bind real quick, and get the job done so you don't have to go back. So let's get into it. I'm going to show you how to do this very easily and very quickly, and you know, at some point in your career, you might have to use this. So remember this. Okay, guys. So using that math we used earlier, we want to have 19 inches from this line to this line. Okay. I added 1 inch on the other side, and I added a half on this side, okay? If you flip this over, I have a half just on that side. So what I'm going to do first is we're going to make a half-half pocket for this half to go into. So let's go over to the brake. So the first thing we're going to do is find our half. Now that's the half that's on the back side. We're going to bend that in like so. Okay. Then we're going to bend that down, not too hard, because you want to be able to get metal in there later. Then flip it over. And then you're going to bend that in. Okay. And what you did is you just made yourself a half-half pocket to accept the other side, okay? So that's it. So between here and this line here, we have 19, okay? That's our 6-inch round pipe. Now, this is a scenario, like I said, you know, let's say, oh, shoot, I'm, you know, in this scenario, I'd be like 4 inches short of 6-inch round. Don't have to go to a parts house. Don't have to go back to my shop and get something. You know, you can do this with hand tongs, too, but I'm going to show you my brake. It's a lot easier. So it's always good to have a portable brake on site, guys. I strongly recommend that any sheet metal job that you're doing, just bring your brake with you. You know, these are very portable, so... Anyway, how do we make this round? You can't just bend it, and that won't work, right? So what I do is I put it in my brake like this, and then I just use the edge on my brake. See that? I just line that up and just give it a little bit of a memory. And you're just going to continue on all the way around. Just bring it out and just give it a little bit of a memory. Little bit of a memory. And you're going to work it all the way around. Now, if this was like 4-inch pipe, something smaller, you would make the bend on it more because it needs to turn more abruptly. So I'm not going to waste you with all this. Let me get this all bent for you, and then we'll be back. Okay, guys, we're back. So let me just... hold on a second here. Making sure that my video's rolling. I couldn't see the cursor. So, you see what I did there? Now, basically you want to do about a 1/2 inch of a relief and see what it did to that. Okay? So the reason why we added 1 inch and 1/2 to the other is you're doing your half pocket on your one side, and then your other 1/2 inch is going to go in there. So then you just put those together like so. Okay? And you just made yourself 6-inch round and got yourself out of a bind. And you can do this with larger pieces. Sorry about that, guys. I got distracted for a second. Or interrupted, I should say. So anyway, in closing on this, just put your relief bends about every... You can do this with hand tongs, too. That's why I said if you have a short piece and you're lacking, you can do this. You can even do it with your bar fold, too, and just put it on the table. And, you know, if you got like a 24-inch bar fold... you know, you can do up to a 24-inch piece of pipe just to get you out of a bind, guys. This isn't something you'd be doing all the time. But in closing, yeah, put your relief cuts about every 1/2 inch. You're going to add 1/2 to one side, and you're going to add 1 inch to the other to make your pocket. You can either, you know, screw this together where it goes in, or you can just tape it. You know, mastic it, whatever. This will get you out of a bind. I've had to do it before. Not often, but I have. But I just made myself a piece of 6-inch round pipe that I did not have before. So let's go back to these formulas, guys. You know, school did help us somewhat. I don't know how good it is these days, but when I was in school, they taught us this stuff. So, and you know, it's not something I just Googled. I learned this in school. I retained it. So, you know, if you want to make 6-inch pipe, you're going to times that by pi, and that's going to give you what you need for your stretch out, your length of metal. 18.85, 19 is close enough. You're going to add your inch and your 1/2. It'd be 20.5 would be your width of the piece of pipe you want to make, okay? Another cool thing that we learned in school, okay? Let's say you have an 8-inch pipe that you're running, and you have to convert it to rectangular. You don't have a ductulator on you. It's, you know, you're going to have to use your brain, right? So, hold on a second, guys. Okay, guys, sorry about the interruptions. My daughter's not at daycare today, so we're kind of working and watching her at the same time. That's why I'm not out at that relocation job today. So anyway, in closing on that, so let's say I took my harness off because I can show it to you better this way. So let's say you have an 8-inch pipe and you need to convert to rectangular. You don't have your ductulator, which does all the math for you. So how do we determine area of a circle? Pi times radius squared, okay? So it'd be 22/7 times your radius of 8. So 8, half of your width is your radius, right? So it'd be 22/7 times radius, which is 4 squared. 22/7 times 16, because 4 squared is 16. Put that over 1 so you can multiply these together. That gives you 352/7. and that gives you 50 inches of area, okay? Well, so then we want to find a duct that's going to work with that, right? So we're trying to convert 8-inch round, right? So 50, what will equal our 50.28? Well, we got 5 by 10 duct will be 50. 4 by 13 duct, wait a minute, I did that wrong. 4 times 13 would be 52. That would be better. 4 times 12 is 48, so that wouldn't quite give you enough area. 6 by 9 duct would be 54 square inches. That would work. 8 by 7. So you could take that with any size, right? So let's say 10-inch pipe would be 22 over 7 times 5 squared. So basically that would convert this to 22 over 7 times 25 over 1, and give you a different number, and give you a different square inches. So little formulas to help you guys. I'll hold it there for a second if you want to take a snapshot of that. These little formulas will help you out in the field. You know, if we don't keep using our brain and we let calculators and you know, Google do everything for us, we're really going to get stupid as a species because our brains aren't working anymore. You know, they go over this stuff in school, I'm sure, these days, but probably nothing like they did when I was in school. So yeah, we got to keep our brain sharp. We gotta keep using it. You know, we're not just monkeys in construction. You know, we do a lot of thinking. We do a lot of thinking on the fly. We have to be quick on our feet, and you know, I think that's why most people age fast, is because they quit using their brain, especially with all these little supercomputers we keep in our pocket. We're getting dumber. So it's very rewarding to do this by hand and write these things down and do it yourself. It's just like when you go to like Home Depot or Lowe's, and you know, somebody stops and asks me, you know, you need me to find you something real quick? Yeah, it's convenient, but you know what? I like to keep my brain working. I'm going to find it myself because that keeps my mind sharp. So I won't harp on that too much, but I think that as a society, we're relying on all this technology to get us by. You know, GPS for when you're driving, all this other stuff. You know, we've driven somewhere 100 times and we still don't know how to get there. It's pretty dumb. So in closing, guys, I'm glad I could show you how to make this. That's what this is all about, is, you know, showing you ways to get you out of binds in the field, and show you some of my little tricks. So thanks for watching, guys. I'll be able to get you a little bit of footage from one of my service calls today. So I got a gas furnace here. First time I'm just jumping it out here at the board. First time the burners did not light up, but the second time they did. So here comes number 3. Let's see what happens here. Flame sensor's okay because it's it's staying on, so igniter's good. Let's see what happens. We're at post purge right now. I'm just waiting for the inducer to come on. Old Frigidaire. Just the wiring diagram. Here's our model and serial, probably in the upper cabinet. Come on, baby. This is why I don't like the gas flex crap. Look at that stuff, man. Looks like crap. Crap. Alright, here she goes. It sure doesn't sound too bad, I guess. Take these burners out and clean them, since they are easy on these units. let's clean our flame sensor. See if we can get it to fire off 5 times in a row. Alright, I got my trusty Milwaukee right angle with my quarter. Take that screw out right there. Take him out. And then of course, you gotta clean him with that. Let's do it. All right, you get the drift. Oh yeah. Let's put her back in. Show you something else I like here, guys. This little guards they make for these switches so you can't bump it with your arm on accident. I wanted to get some of these. They don't have it for the light switch, but they have it for the furnace switch. That's pretty cool. All right, we're back in. She's polished with the $100 bill, the Benjamin. Let's fire it back up. Switch close. There's the igniter. Come on, gas valve. There's one. Okay, number 2 commencing. That was just me making that noise. That coil. ADP, Stone Mountain, Georgia. There goes the pressure switch. There goes our igniter. There's quite the delay in this gas valve. Let it run a bit, make sure it stays on. Okay, let's put him in there for good luck. A good luck charm right there. Sure it stays on. Make sure our blower's kicked on too. Guess I could get my clamp meter on there. Hold on, I can't really hear if it's on or not. Alright, we're getting 3.86 amps. And that's not our blower, that's our full line. Hold on a second here. Never mind, I'm a dummy. That was our blower. Set the light on. See that? 2.74 amps. So let's kick this back off again. Got our burner stand on. Let's go run it through the cycle again. Let's watch our amps go from 0 to nothing when our blower kicks on. All right, initiating the inducer, so we have no amps, so we know our fan's not on. Let's see what our inducer amps are. We are, damn, this light doesn't show up good. So we're 0.85 amps on our inducer, and it's rated at 1.1, so we're good there. Let's go back over to our fan. He already kicked on. Post purge. It's taking a while to get that pressure switch to close. Might clean all these hoses up too while I'm here. There it goes. It's just doing its post-purge stuff. I'll be right back. So what'll happen with these is it'll go through its post-purge, and our fan will kick off. You'll see our amps go to 0 here, and then our inducer will come back on. So right now we just have fan on our post-purge, and it'll start the cycle again to get our heat going. So wait for that, and I'll be back with you. This was my handiwork here when I was here a couple of years ago. There's huge holes in here just shooting all kinds of heat out, so I taped that all up good for them. Some mastic tape. It's ugly, but it works. Alright guys, post-purge is done, our fan is off. Our blower fan. Here goes our inducer fan here. Inducer motor, vent motor, whatever you want to call it. Let's go through our sequence again. So we're going to hear our pressure switch click. Not there. There it goes. If you heard that. Let's go down here. Should get an igniter. There goes our igniter. And we'll hear this guy click. It's a really slow operating furnace. There we go. Let's make sure she stays on. So there's a fan limit switch in the air side of the unit. It'll kick the fan on once the heat exchanger gets to a certain temperature. That's when the fan kicks on. So let's wait for that. When these burners going, it should trigger the fan shortly. So basically, there it goes. Ready to click, or the relay click on the circuit board there. And there goes our blower. Alright, now the last thing I'm going to do is go inside and just make sure the thermostat's doing what it's supposed to do, because I have it jumpered out from bypassing the thermostat, so we always want to make sure it works per the thermostat as well. So let's go do that. Let's pull my jumpers off. Okay guys, I got my jumpers off there. That's one thing you never want to forget, or you're going to have a really unhappy customer with a hot house or a cool house. Cold house. Always remember to take your jumpers off. Guess how I know that? I've done it before. So we're waiting for our post-purge now. Basically what happens is the fan will stay on. Usually it's about 90 seconds to get any of the excess warm air out of the ductwork before it kicks off. That does a couple things for you. It keeps the ductwork from popping so much, and just it wants to utilize all the warm air it's produced before it shuts off. So right now we're calling for heat on the old thermostat. Wait for that. Okay, we're back to our heat initiation sequence. Blower is off. Vent motor, inducer motor is on. Another lucky charm in there. Don't let me forget him. Wait for this pressure switch to click and shut. Hear that diaphragm get pulled in. There it goes. Go down here to our igniter. Hopefully, if you're not familiar with furnace sequence of operations. This is helping you some. Should give this guy to click here shortly. I don't know why it takes this furnace so long. There it goes. Fire in the hole. Make sure she stays on. Get this guy out of there. Put this panel back on. I'm going to make sure she stays running for a while. Actually, let's wait for our blower to kick on. Let's hear this relay click. Which one of these relays is the fan relay? I would think it would be up here by where the fan caps are. There it goes. Easy cheesy. Alright, put this panel back on. And I'll make sure she stays running for a bit. I'll put the thermostat, see where the customer's thermostat is at, and get on out of here. Alright guys, it's been a good 10 minutes or so. She's running good. No issues. Let's go inside and check the thermostat. Alright guys, that's a wrap. Got my sticker on there. It's one of my older stickers. It doesn't have the lines for writing stuff on, but she's selling the house, so at least the new people will know where to go if they have any issues with this old system. AC is really old, so there you have it. Let's get out of here. Alright guys, barely get to see this pretty face, so I thought I'd show it to you real quick. Well, sometimes you get to see enough of it. My wife gets tired of it. So yeah, hopefully you learned a little bit about gas furnace sequence of operations there. I'm not the best teacher, but I do my best, and hopefully that taught somebody who ends up watching this video how it's done. So anyway, I'm out of here. I didn't get anything on my first service call. I think that was just a dirty coil. I'm gonna have to come back when I'm equipped and I don't have frozen hoses to where I can give that system a thorough cleaning. So I'll be going back to my first call today. Both out here in beautiful Prineville, Oregon. If you've never been out to Central Oregon, if you live on the West Coast and never have, definitely come on out here. It's beautiful, lots of recreation, lots of things to do. So that's a wrap. Thanks for watching, guys. I appreciate it. Hey guys, Seton HVAC here. So in this video, I'm going to go over with you how to simplify your low voltage wiring on residential HVAC systems. And what I normally use on all my jobs, no matter what type of job I'm doing, is 1810 wire. Now what that means is it's 18 gauge wire. Each of these wires is 18 gauge, and there's 10 of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 18 gauge / 10 wires. So let's go over to our diagrams here. Let's start with the gas furnace. So let's say you're doing a simple single stage gas furnace. You're going to have an R, a C, a W, and a G. Sorry guys, I put G at the end because I almost forgot it. So it's there. So R, C, W, G. Now how would you wire that up? So it would be the same way between the gas furnace and the thermostat. So you take your 10 wire here and you would do green, red, white, and blue. Okay? That's all you would have are those 4 wires. Okay? So where do they go? Okay? It's pretty self-explanatory. So red, sorry guys, I'm trying to do this without my chest mount on, and I should have that on. Let's finish this up with that on. Hold on a second. Alright guys, real life stuff here. I tried to wing it didn't work. So let me show you. So on your basic gas furnace, you're going to have R is going to be your red wire. Common is going to be your blue wire. W is going to be your white. And then all the way down here, sorry, they're supposed to be together, is your green wire to G. That will do your basic single stage gas furnace, okay? Now, let's say we're doing a furnace with AC. So you're going to have those same 4 wires, red to R, blue to C, white to W, and G, green to G, and that is your fan, okay? Now let me tell you what all these mean too. So you have 24 volts, 24 volts common, that completes your 24 volt circuit. W is heat. Yellow or white, sorry, Y is going to be your yellow wire, that's cooling. Y2 would be if you had a second stage of cooling on a 2-stage air conditioner. W2 would be if you had a second stage of heat on your gas furnace. That would be, I'll tell you what wire we'll use for that. And then G is your green, is your fan. So here's the colors I like to use if we have a second stage of gas furnace. Sorry about the stammer. I'm trying to. I kind of messed my diagram up. But so what I like to use for my second stage heat normally is gray, and I'll tell you why in a second. And and the color doesn't really matter, but pick a color and stick with it and do it on all your jobs. I know there's guys say there's industry standards, but there really isn't. Okay, so W2 for gray. And then if you have a second stage of cooling, well, let's do first stage. So first stage is always going to be yellow, okay? Always yellow, every time. Do not ever change. So what I like to use for my second stage on cooling with my 10 wire is pink, okay? So we have our 24 volts, hot is red. C is our 24 volts common, blue. W is white, and that's our first stage heat. Y is yellow, that's our first stage cooling. Y2, I like to use pink, that's our second stage cooling. W2, that's gray, that's our second stage heat. And G is fan, that's always green, okay? So let's go over to if you had a heat pump that you were going to wire. So these ones are all going to be the same except for a couple different things, okay? So you're going to have, your green for your fan, G, your 24 volts hot, red, your 24 volts common, blue. Now this is where it's different. So this is, in a heat pump, you have what's called backup heat strips. So on some heat pump thermostats, this will be W, or it'll also be auxiliary, okay? So that's still going to be white, but that's your backup heat, and that's also your tempering heat for when the system goes into defrost. Still a white wire, but it's nice to know what that actually does. Y in a heat pump is yellow still, but we call that first stage compressor because all that's doing is energizing your outdoor unit, okay? Just like in an air conditioner, but it also produces heat. Y2, second stage compressor, second stage condensing unit. W2, if you had 2 stages of strip heat and you wanted to stage them, that's what that would be for. Now O, that's different. So that's going to be your orange wire here, okay? Always use orange. That's for your reversing valve, or what some people call a switchover valve. That's what switches your heat pump between heating and cooling. And then lastly, you have usually a couple of S terminals on your thermostat for a heat pump if you have a heat pump that does it. Now some of the Wi-Fi ones don't because they do it via the internet. This is for an outdoor sensor, okay? Call it an ODS. So you'll have a 2-wire sensor that'll go outside and it'll wire directly. Now that's why I leave the black and the brown left. It's the only thing that's not being used here, okay? I like to use those two every time, then I don't screw it up. So in summary, let's go over here. So G, green, and I didn't write my reversing valve in here. Let's just put it right there. It's going to be orange. And let's just put RV there. And then we can also put, this can be auxiliary for your heat pump. So you have G is always going to be green for your fan. R is always going to be red, 24 volts. C is always going to be blue, 24 volts common. Then we got your white there, auxiliary. W. Y is yellow. That's always going to be first stage. I want it right there. I don't have room. First stage condenser. Y2, pink. Second stage condenser. W2, I use gray. And that's always going to be your second stage heat. And then you have O is going to be orange for your reversing valve and a heat pump. And then your two outdoor sensor terminals. S terminals usually on heat pump thermostats. I like to use black and brown. Now this is just for 10 wire. Sometimes guys will pull different. I do the same thing every time, and it keeps everything uniform. So if you do it this way, you'll be in good shape and you won't mess anything up. If you want me to get into different systems and how you wire the air handling units, and then show you how to wire the outdoors, I might just take you to my Bosch system and go over that one day. But this is a good breakdown of how you wire these up and how I use my 1810 wire. Okay? All right, guys. Thanks for watching.
Oh, yeah. Yeah, baby. Yeah. Ow!
Hey guys, good morning. Seton HVAC here. So in today's video, I'm going to show you 4 different scenarios here on company size and why it's important to keep your overhead down and make the company more profitable and pay your employees more money. So let's start with the first one here. So a 3-man or woman company, just a small little company. I'm going to show you that scenario. I'm going to show you a 1-man band, 1-woman band company, 12-man company, and then a 20-man company, how that overhead factors into your hourly rate, your break-even, basically. So that's what I'm showing you. I shouldn't put hourly rate there. That's your break-even number that you need to make per hour. So I'm going to show you all 4 of these scenarios. So what's important when it comes to keeping costs down, making your company more profitable, and making it more money, and your employees more money. So efficiency is most important. Everybody must be efficient. That's, all these guys think that their boss is being a jerkwad, but honestly, if you're efficient with your work and aren't wasting time, you're going to make more money. That's just the way it is. I've owned 3 or 4 businesses, so I understand it wholeheartedly. It's not me being a jerk. It's just the way it is. So that efficiency equals lower overhead, okay? Sorry guys, got distracted by the little one. Every time I do a Saturday video, that happens. So efficiency equals lower overhead, okay? We're trying to keep those costs down as far as just, things breaking. There's all kinds of factors in an HVAC business. Trucks breaking down, make sure you get the oil changed. Are you organized in your van? Just little things that, and this is why it's important for you to be efficient, because not only does it keep the overhead down, it gives the boss a little more meat on the bone. If he's a generous guy like me, he can give you guys more bonuses, spiffs, all kinds of stuff. So efficiency is key to keeping the overhead down. In turn, that's going to keep the hourly rate down that you're charging the customer. It's going to give you more business. So I'm going to break it down for you how these 4 different scenarios and show you why it's important to be efficient and keep that overhead down, because it keeps your hourly rate down, which is very important for getting more business. Doesn't mean you're cheap. It means you're efficient, okay? So let's go over that right now. Okay, guys, the point of this video is to come to this conclusion, okay? So what are we looking at here? We are looking at your estimated hours that your employee is going to work, or estimated days that your employee is going to work per year, okay? So, taking out weekends, vacations, etc. A good number to shoot for there is 220. and then you times that by your 8 hours times 1,760 hours per year times X. What do you want this number to be? What do you want your employee to make you in profit per hour per year? Okay, and that'll be your profits. Yeah, profit per employee per year. So that's a number that you need to come up with. Okay, you need to know what you want to make on top of your break even, which I'm going to show you that. So everything after this short little intro video is going to be your break even number that I'm going to show you. Then you would add this number on top. So let me show you an example. So you got your yearly days worked per employee times their hours would be your 1,760. Let's say on top of your break-even number, you're going to put $30 per hour. So that employee is going to make you $52,800 a year. Now that's pretty extreme. If you especially have a big company, you're probably not going to make that much per employee. So that number would be smaller. For me as a one-man band, I can add somewhere $30 to $40 because I want to make that. You know, I want to make that profit and put that back into the company. I might need to buy a new van next year. So let me know if that makes sense to you, and let's get started with some of these other numbers. I'm going to show you your break evens and how that correlates with your overhead, etc. So let's get into it. Okay, guys. So we got 3 different scenarios here on how you would calculate your hourly rate for the year for your HVAC business. And you know, some companies tweak this for different times a year. You know, sometimes they tweak it for when, you know, if they need to lay somebody off, then this formula changes. You can change your hourly rate, and a smart company does this. So let's go over this. So let's say you have a small company that's got 3 employees. Let's say your yearly overhead, that's everything that you have to pay, is $626,716. I just came up with random numbers. That's why you need to know what you're spending every year. As soon as you know this number, you can do this formula. So let's say your guys work 220 hours a year. Okay, so if you were working, 5-day weeks, sometimes we work Saturdays too. Times 52, that would be 260. You know, you got to factor in vacation, and sometimes guys just ain't worth a shit for a day. That's honest. So 220 is a good number for me. That's what I would put if I had some employees, which I do not. So you take that, divide that by your man hours per year, and that would give you your daily expenditure on that employee. Okay. Now, if you have 3 employees, you got to take that number and divide it by 3 because you're dispersing that throughout 3 guys, right? So you take your 3 employees, so that number comes out to $9.49 8-hour days. And obviously we work more or less than this sometimes, but this is a good average to have. And then that gives you your hourly rate of $118. That's a pretty good structured company there. If you're able to put your hourly rate at $118, that's pretty darn good. So also you got to figure what you want to make for profit too. So this is your break even is what I'm trying to give you here. I'm not giving you what your hourly rate should be. Let me show you a scenario for me as a one-man band. So this isn't me. This number's not correct. I'm not going to divulge my stuff here. But so let's say my expenditures were $317,000. You know, I tend to work more than if I worked for somebody. So I got to factor in all that time. So let's say 240 hours throughout the year comes out to $1320.83 per day, and then divide that by 8 hours, and that gives me $165.10. Now that would be my break-even number. So that's not structured very well either. And I guarantee you that my numbers are better than this because I don't charge that much and I do very well. So anyway, that's just so then you'd want to figure out what profit you want to make throughout the year, what you want to pay yourself, and you'd put that on top of that. Then you'd average that out by your 240 work days, and then that would give you your hourly. And I'll show you how to do that in a second. And then your large company, let's say they make their overheads $5,176,500, and let's say those guys average out at 240. I think this is actually supposed to be 220, so let's say that's 220. I changed it, and then that would be $23,529.55 per day, and then they divide that by I didn't put it here. That's 12 employees, okay? I don't know. That's not really a large company, but larger, okay? So divide that by 12 guys. That'd be 1960, 79. Divide that by 8 hours. So that'd be 245.09 per man hour. So this would not be a very successful company if that's how they were structured. Now let me show you how that changes. Let's say they made a little bit more money and they had more employees, okay? And I'll show you how that changes their hourly rate, and that would be a better structured company. So let me show you that. Okay, guys, let's look at this large company again. So let's say they went through some retooling and they restructured their company and they were able to become more efficient. And that's why it's so important to keep your overhead down. So let's say their overhead burden per year is $5,576,231. Okay, let's divide that by our 220 days. So per day, their overhead is $25,346.50. Okay, that sounds like a huge number, doesn't it? But I mean, for a company of 20, that can easily happen. Figure payroll and everything else, vans, gas, etc. So let's say they now have 20 employees. So they're, their overhead didn't go up a ton, but they still have, then they have 8 more employees. So that's cool. Now they're going to make more money, right? So you divide that by 20. So that's $1,267.32 per employee overhead per day. So then what you do is you take that divided by 8, and now look what that did to their hourly rate, or their hourly break even. Okay, so they figure out what they need to make on profit on top of that. That's after paying all the employees, doing everything, what goes into the business. So this number doesn't have to go up that much if you factor it out through a whole year. They're going to make plenty of money on profit to put back into the company, and that's why it's important for companies to be efficient. That way they can offer profit sharing and all kinds of other stuff. This number includes all your medical benefits and everything too, so you don't worry about any of that. This is just money, icing on the cake, and I would assume that the owner's salary is factored into this. Everybody, management, whatever. So just want to show you guys how that's done, and yeah, it's pretty cool. One-man band's slightly different. This number's, I'll do a different scenario for this at some point, but let's say this is me and I'm charging $165. I could probably up this to, $200 an hour, and that's 35. So I'm just icing on the cake. I'm already paying myself. I'm making money. This is just profit that would be going back into the company. See how that works? So, yeah, let me know if you guys think this stuff's interesting. I can get more into the numbers. I actually do some real world scenarios because I know what mine is, and I'll show you what I'm doing. I'm totally transparent about that. So let me know, guys. Thanks for watching. Hey, happy Saturday morning, guys. So I got a little bonus Saturday morning call for you, and I'll tell you the backstory here in a second. But a little more troubling is my wife is taking my daughter to the pizza parlor today, and I asked her when, and she said, I don't know yet. My friend hasn't called. Early evening sometime, probably like 2. What's wrong with that? She thinks 2 o'clock in the afternoon is early evenings. She got pissed at me for correcting her. I consider early evening starting at about 5, right? 4 o'clock would be late afternoon, don't you think? Anyway, I've gotten a little bit of a fight over that. She thinks I was correcting her all the time. I'm like, well, when you're wrong, I'm going to correct you, right? Anyway, details coming on today's call, and I'm going to get some footage for you if the customer's not breathing down my neck too much. Okay, guys, I'm out here. So she got screwed on this deal. They left the disconnect off to her heat pump, and I don't think there's a valid reason for it. So let's get into the access panel here and see what's going on. All right, let's check this guy out. Let's check our Herm. Nothing. Fan. Nothing. Let's go get her a cap, see if we can get this thing going for her. Alright guys, we got the new cap here. Let's check out the Herm first. Let's see, it's right there. 48. And let's check out our fan. 5.2. Let's put it on, see if this thing runs, see if these guys are full of shit. Okay, I gotta go get a bit tip screw so I can get that screwed in, but we're running. See if our suction line's getting hot here. Let's give that a second. I'm gonna go grab my gauges and see if there's anything wrong with the pressures. They gave her a $4,000 repair bill for this. $1,500 just for a condenser fan motor. Unbelievable, huh? I'm gonna go get that bit tip screw and then I'll grab my gauges while I'm over there. Okay guys, we got the old train charts here. As per usual, I drew my lines. So we're on true suction there. We're at about, let's call it 42, 43 on our suction, and our head pressure is about 220. Let's go over here. Outdoor temp is about 27 degrees. All right, my eyes are watering. It's cold out here. And that puts us at about right in there, 43. Let's look at our head pressure. Each of these squares is 10, so put us around 200 or so. So nothing wrong with this unit at all. Got him in there, snug as a bug. Went and got a bit tip screw and tighten it since the new capacitor is smaller. Let's go check our temps inside and get out of here. I'm going to button this up first. Okay guys, so I'm going to show you the details of what the other company tried to do when I get back home today. Really trying to take advantage of people, and I really am tired of it. So I'm heading over to this fireplace that I installed for this lady. I don't think I got any footage of it really for you, but I'm just going to double check her millivolt readings for her thermopile, because her pilot keeps going out. I don't know why, and it's very sporadic why it's going out. We're going to stop and do that, but that's kind of a sidebar to today. I want to stress the nonsense that this company is doing out there. It's one of the big companies in town, so stay tuned. Okay guys, I am back for the day. It's almost 2 o'clock in the afternoon, so it must be early evening, huh? According to my wife. Okay, that joke's old. I've been thinking about that all day. But what I have here is the other company's estimates for repair. Now, it'd be easier if I just go over this piece of paper with you. Unbelievable. And I'll tell you what I ended up charging her. So let's flip this around. So let's see here. Let me go over to, hold on, I gotta find a good flat spot here. This will work. Okay. Oh, let's go over here. Alright, so I blotted out all the pertinent information. I don't want to defame anybody. So this company, what they're doing is they're doing what's called complimentary inspections. Now, if you're sending your guys out for free, you should know that they're going to be charging you. They're going to try to find something to charge you for, I should say. So let's just start off here. This was only 2 days ago. So you see the date on it, 1/16/2025. Like I said, complimentary inspection. So he arrived for a complimentary inspection of the HVAC equipment. No issues were reported upon arrival. Customer had to leave home for work during inspection. EF, that stands for electric furnace. I inspected the air filter, inspected the evaporator coil, found the coil is very dirty with pet hair, verified proper free spin on blower wheel, and inspected motor to verify no signs of leaks. I verified all electrical connections are fastened properly and inspected to ensure no signs of arcing. Tightened line connections at furnace breaker, ran electric heat, found only one strip was fully powering on. That's a lie. Pulling 20 amps properly. Bottom section was only pulling 15 amps out of 40. That's a lie. Verified proper amp draw from blower motor while operating. Heat pump. Found the condenser fan motor is leaking oil. Tested microfarads reading on capacitor. Found the fan terminals completely discharged. Contactor is pitting, showing signs of wear. Not true. Verified all electrical connections are fastened properly, inspected to ensure no signs of arcing. Verified the condenser fan motor will not operate due to failed capacitor. That is true. Could not run the heat pump as a result. Not true. Replace the capacitor. Turned off power at the heat pump, switch thermostat to run on electric heat only to preserve the life of the compressor. Now that's funny. At this time, could not verify operation of condenser fan motor or heating via the heat pump. BS. Here's what he quoted her. $347 for a dual run capacitor. I'm going to assume that's a Titan or a Mars or something. You guys know how much those cost. I think that's pretty ridiculous. But we'll give him a pass on that one. 1-year warranty. Now, if you want to do a Turbo 200, the universal capacitors, he'll give you a 5-year warranty. That makes it $432. Now, this is where it starts getting real crazy. $1,535 for a heat strip kit. I believe I can get those for about $200 and have it installed in about 15 minutes. So, he is a vulture, this guy, or this company. $396 for contactor replacement. Yeah. $1,533 for a condenser fan motor replacement. That is outrageous. I know how much the condenser fan motor costs for this, and I don't think I could inflate my cost anywhere near that. Anyway, he could not reach customer after inspection, called and left a voicemail, sent a text message explaining my findings on a complimentary inspection. Sorry, man, you're going to have to spend $4,243. Woo! I mean, if they did all that, well, you could take one of these off, so it's still pretty close to $4,000, a little under $4,000. Crazy. And it was a complimentary inspection. Worked fine before they got there. He had to shut the heat pump down. See, nope, no charge there. So what had happened was she... hold on, let me turn this back around. So what had happened was she had lost my phone number and had to call them out because she couldn't find out how to get a hold of me. It's been a few years. She must have lost my messages or my invoice or whatever. So she called them up. They came out and did all that nonsense. And then she looked back in her text messages, finally was able to find me. I don't think she could remember my last name, so that's why. So she called me up and I said, "What'd you do, lose my number?" And she said, "Yes." And called me and I saved her. So, so my bill, and you guys probably think I'm really cheap for this, so I charged a $159 trip diagnostic, and then I charged her $36 for the capacitor. $195 out the door. Saved her big time, and I'm happy that I was able to do that. So that's a wrap on this video. But I'm not going to name the name of any of these companies because I don't want a defamation lawsuit. What I can tell you is you can figure out for yourself, if you live in the state of Oregon, they have big red and white vans everywhere. That's all I'm going to say. And it's got a letter of the alphabet that is pretty prominent on the side of their van. So I'll just leave it at that. Until then, hope you guys enjoyed the video. I'll see you next time.